Assalamu alaikum warahmatullahi wabarakatuh. My topic is about waiting lines and queuing theory models. I will start by introduction of a queuing theory, followed by waiting line costs, then characteristic of a queuing system, and I will then discuss different types of queuing models available represented by MBAR, MBAR 1, MBAR, MBAR M, MD1, and finite population model. What is a queue? A queue is a line of people, vehicle, or any other things awaiting their turn to be attended to or to proceed. I am sure at least one a day you are in a queue. Examples for a queue, one would be a queue or a line waiting for lining up to pay in the supermarket or lining up to check your balance account at ATM machines. It's not only present for people, it can be also for airplanes waiting their turn in order to fly at the airports. Then we have jobs or products which are waiting, and then the most annoying of all would be traffic. So queuing theory determines the measures of performance of waiting lines, which can be used to design services. It's not only an optimization technique, and because waiting cannot be eliminated completely without incurring inordinate expenses, the goal of giving theory is to reduce its adverse impact tolerable levels. So, queuing theory would not give you a solution, but would give you the measurements or analysis in your queue or in your different lines. For example, when you are paying at supermarket, you have a server and you have different customers, so the supermarket would be the source of the line order. The service time would be the amount of time that the cashier would take to serve. Basically, it's under negative exponential distribution. Then the inter-arrival time between different customer, for example, 2 minutes, 4 minutes for the next one, and then 5 minutes for the next one is called inter-arrival time, and it would follow a Poisson distribution. Now let's try putting into servers into servers and one line. The two servers would be the service facility. Then the one line is called the queue or waiting line. The people in the queuing or waiting lines are called the arriving customers. And the one who just finished being served by the server is called departing customer. So the queue or a waiting line plus the service facility is called a system. Most of the time, the waiting line problems are mostly focused on whether the size of service provided is ideal or not. Service providing can be managed by the authority themselves. They can provide two extreme services at two extremes when they can hire many people or many systems. Which provide a huge service facility. That means their service costs will go up. Or they can provide the minimum number of service facility possible. In that case, the service cost will go down, but there will be a lot of people who will be dissatisfied with the minimal service provided. In any service facility, what is evaluated is nothing but the total expected cost, which is the sum of service cost and the waiting cost, all to minimize the total expected cost. So if we increase the service level here, what is the cost of providing service will increase at the same time. Cost of waiting time will decrease, but then total expected cost follow a curvature structure, as in here. And optimal level is minimal most total expected cost level, where you can get the minimal total expected cost. An example, a three reverse shipping company, they are providing facility for docking at some river. They have on average 5 ships arrive to unload the cargo. If a ship is ideal, that means the cargo is not unloaded. It's ideal. then it costs around $1,000 per hour, and if they put more staff they can unload quickly, but at the same time the staff has to be paid the salary, so the company want to determine what is the optimal number of teams of staffers they want to employ to minimize their total expected cost. So the number of teams they can employ is 1, 2, 3, 4 here. Average number of ships arrive per shift is like 5 average time each ship wait to be unloaded. If it is one, they have to wait for 7 hours, and if it's 2, they have to wait for 4 hours. If it's 3 is 3 doors teams, then they have to wait for 3 hours, and so on and so forth. And total ships hour lost per shift can be found by just multiply the total average hours multiply by the number of ships. So just multiply 7 by 5, which is 35, and 5 into 4 is 20, and so on and so forth. Similar, what is the cost per hours per ideal ship? What is like $1,000? It's given in any scenario. Then you multiply the total ship hour lost multiplied by $1,000 each, so it will be 35,000 in the case of one team of Steves, and 20,000 if there is 2 Steve Doors teams, and so forth. For the salary of each team in a single team is given $6,000, and 2 teams it will be 12,000, and 3 to 18,000, and so on. So add the salary plus the amount of waiting cost, which is 35 plus 6 is 41, 20 plus 12 it's 32, and so on and so forth. So in the total expected cost, the minimal most one is optimal cost. That means the company goes for the 2 Steve Doors teams, which will be cost effective for the company. There are 3 important components of a queuing process, which is arrival, the rate at which people arrive to the system. It's something called calling population. Second is the waiting line. Is a queue analyzing the waiting lines can help developers and managers to find out whether a system is optimal or a system is a cost effective or performance effective. The third is the service facility, that is a service provided. Based on all these components have a certain characteristics which can be modeled using mathematical queuing model. For the arrival characteristic, number 1 will look at the size of the calling population, whether it is unlimited or infinite. For example, as I mentioned previously, supermarket, when people come to the supermarket, the number of customers who come is small compared to the total population. That is called size of the calling population, which is unlimited. But instead, if a company having only 8 machines that can be handled with repairing or maintenance, so the number of emissions is 8, so this is limited, it's a finite population. Second, a pattern of arrival. Arrival pattern can follow a pattern of some method or arriving randomly, or it can be random if the arrival is random. Then generally it is represented using Poisson distribution. Arrival, customer normally most queuing model assume customer are patient and will wait in the queue until they are served, and don't switch line, but some of them are joking. That means a customer enter one line and then switch to a different line in effort to reduce a waiting line. There is another case which is called bulking, which means some customer come look at the surface, they see a huge queue, so they refuse to join the queue and just go. The third one is called renanging. Here a customer come and wait in the queue for some times, then he becomes impatient and taking too long, so decide to leave the queue without getting any service. Waiting line characteristic, it can be either limited or unlimited. If we are talking about a number of tables in a restaurant, that is limited number. But if we talk about number of cars that can be in a toll booth, it can be unlimited. So queue discipline refer to the rules by which customers in the line receive a service. First in, first serve is the most common rules. For the service facility, service systems are classified in terms of number of channels or servers and the number of phases or service stop. One single service serving everybody, that is called a single channel system, or multiple servers, all of them are fed by a single common waiting line. One line wait and then go into any encounter, that's like a multi-channel system. Second is patterns of service time, that is called a single phase system. Every customer will get served by one single server and then they go. Or multi-phase system, a customer come and do some job in one counter and then go to another one. That means his job or their job in different more than one service, which called a multi-phase system. The diagram here show a single channel. They arrive and then they do one job and then they go in a single channel, single phase system. Single channel multi-phase system in the second one. They arrive and having first job, then go to the next channel and waiting, then go and do the second job. So multi-phase having two type of services. Multiple channel single phase, people come and do one job of the three different facilities, but not all the three. So choosing only one. A multi-channel multi-phase, arrivals go through a different channel and for each level they will have one serve or one service, then go to the next level, next service, and so on and so forth. To identify all these models using the candle notation, these notation represented using three symbols called patterns of arrival, service time, distribution, and number of services channel open. M means boson distribution, D means constant or deterministic, G means general distribution for the mean and variance. So let's start with the single channel model, boson arrival, exponential time, that represented by M bar 1. Boson arrival, M in the first, exponential surface, M in the middle, and a single channel that is 1 at the end. There are some assumption of this model. Arrival are served on a first in, first serve basis, no bulking or reneging. Arrivals are independent of each other, but rate is constant over time. Arrivals follow a boson distribution. Service time are variable and independent, but the average is known. Service time follow a negative exponential distribution. Average service rate is greater than the average arrival rate. So these are the assumptions. If they are met, then the developing a series of equations that could be used to solve a queuing operating characteristic. Let's start here with the symbols. We have lambda, which is represented mean number of the arrival per time period. That is the arrival rate. And the mu, which is the mean number of customer need to be served. This is a service rate per time period. The time period here of the arrival and the service should be the same. Otherwise, we cannot use them in the same equations. To find average number of customers or a unit in the system, that is L equal to lambda divided by mu minus lambda. To find average time a customer spend in the system, it's a W, that is 1 divided by mu minus lambda. To find average number of customer in the queue, LQ, which is lambda squared divided by mu multiplied by mu minus lambda. To find average time of a customer spend waiting in the queue, which is WQ equal to lambda divided by mu into mu minus lambda. To find the utilization factor, how much utilizing the service, which is called as rho, that is equal to lambda divided by mu. Calculating percentage ideal time, how long a probability that no one in the system, so the system is idle, it's a B0 equal to 1 minus lambda by mu. To find the probability that the number of customers in the system is greater than k, that means B of n greater than k, which is lambda by mu to the power k plus 1. An example is the scenario of Arnold as a campaigning mechanic. He can install the mufflers at a rate of 3 per hour and the customer arrive at 2 per hour. So lambda is equal to 2 and mu equal to 3, both of them having per hour as a time period. To find all of them by applying the equations L, W, LQ, WQ, rho, and P0. And we got all the value. To find the probability of more than k in the system, we can start with the 0 until 7. To calculate the probability of 0, that is 1 minus P0. So that means n greater than 0, meaning 0 has to be excluded. And if we see number k equal to 3, that means 19.8% chance that there are more than 3 cars in the system, so it is 0.198. To apply the cost into the picture by calculating the economic situation of this system, the total surface cost will be equal to a number of channel multiplied by a cost per channel. That is M into CS. M is the number of channel and CS is the surface cost of a labor cost. To find the total waiting cost in the system, total time spent waiting by all arrivals multiplied by cost of waiting. To find how much time are spending, it's the number of arrival into average wait per arrival into CW, that is lambda W into CW. And then to find the waiting time in a queue, just to change W into WQ, which means lambda into WQ into CW. To find the total cost, that is sum of the surfaces cost plus the waiting cost, so it is MCS plus lambda WCW. If it is based on the Q, then it is MCS plus lambda WQCW. Where lambda is arrival time and mu is the surface time, they are all in the same time period. To find the total daily cost, if the waiting cost is given CW, which is $10 per hours, so multiply 8 hours per day into lambda, which is 2 into WQ, which is 2 over 3 into 10 to get the value. If the mechanic surface is charged like is paid $7 per hour, so we find the surface cost 8 hours a day into M, that is number of mechanic only 1 into CS, the surface cost that is 7. Then we add the result value to cost waiting to get about $163. That is the total cost of a queuing system. If the company thinks of hiring a different mechanic who can do the job faster, so here the arrival rate is the same, that is 2, but the surface rate is increased from 3, it has become 4. We need to calculate the L value, which is the average number of cars in the system, and W, average time a car spent in the system, and then average number of cars in the queue, average waiting time per car, also percentage of the system is busy, and the probability that there are no cars in the system. To find the total cost of the system, we will multiply waiting cost, which is 8 into lambda, that is 2, into WQ, which is given quarter, into CW, that is 10, and we get the value. For the new mechanic, it charges $9. So we just multiply the value into M, CS, and this is the amount we get here. So instead of the first one, if we apply this, that the cost of the system has gone by 10. It was 136, and here it is 112. Now the total time spent waiting for 16 customers per day, where arrival rate is 2 and the number of working hours is 8. So we have 16 cars per day, and every car is waiting 2 by 3 hours per car. So we will get 10.67. But if we go for the second approach with the faster mechanic, the waiting time is 1 per car owned by 4 hours, a quarter an hours multiplied by 16 cars, and we get here 4 hours. So we are saving some money because the time with the first mechanic was $163, and the second mechanic is 112. So we are saving about $51. If we go for the second time, then we might think reducing the waiting cars and is only a way to reduce the cost. There are also other ways, like reducing the unit waiting cost will reduce the total waiting cost, and this might be less expensive to achieve than average wait W and WQ. The next model is a multi-channel model, both on distribution arrival, that is the first M, and exponential service time, that is the second M, and a multi-channel for the last M. As a previous model, lambda is the average arrival time and mu is the average surface rate. Assumption here follow the same as in the single channel model, so no differences. The equation for a multi-channel queuing system given M, lambda and mu. Here the equation for the probability of 0 customer in the system is given, as you see here. And there is a condition that M into mu should be greater than lambda. And here the equation for the average number of customers or a unit in the system, and the average time a unit is spent at waiting line or being served in the system. Equation of LQ, which is the average number of customer in the queue. WQ is the average time a customer is waiting in the queue, that is W minus 1 divided by mu. B is the average number of customers or a unit in the line waiting for a service, which is basically the utilization rate. To apply these assumptions, here an example, the company Arnold want to investigate opening a second garage bay. He would hire a second worker who work at the same rate as his first worker. The customer arrival rate remains the same. Service rates C is 3 per hour, M is 2, lambda is 2, and mu is 3. Here N become 2, it's not 1 anymore. So we apply these equations and get all values. If we have one single mechanic whose serve rate is 3 cars per hour, 2 mechanics here, both of them serving at 3 cars per hour, or one faster mechanic who serve at 4 cars per hour, and the value are given for B0, W, LQ, and WQ. The second surface bay reduce the waiting time but will increase the surface cost. So how much is the total daily waiting time? 8 into lambda, which is 2, and WQ is given and CW is 10. We get the value of waiting cost, that is about $7. For the surface cost, that is 8 hours per day into M, which is 2, because we have 2 mechanics, into CS, that is 7, so we get $112. If we add both values, we get about $130. 19s. So the fast mechanic is the cheapest option. The third model we have is M bar D bar 1. M is a boson arrival. D is a constant that we stand. 1 means one single channel. The constant surface time means they process it at a constant time. It is not average value. We can calculate the value LQ, WQ, L, and W, and we will find these are lesser value compared to the variable surface time. So both the average queuing length and the average waiting time are a half compared to the previous one. Here the average length of a queue, LQ, that is lambda squared by 2, so it's half of the previous one. 2 mu into mu minus lambda. Similar, the average waiting time in the queue where lambda at the numerator. To find the average number of customer L equal to LQ plus lambda by mu, and average time in the system, that is WQ plus 1 by mu. Here is a company example given that they collect aluminum cans and glasses bottles. The truck arrives at an average rate of 8 per hour. So this follow a boson distribution. A truck drivers wait for 15 minutes before they can empty their load. Drivers and the truck cost so many hours for waiting in the queue. So per hour they have to pay $16. If they are waiting in the queue, and if we replace the system with an automated machine which can do the truck load processing quickly at a rate of 12 per hours, and the new compactor will charge $3 per truck unloaded. If we want to calculate the current waiting cost per trip, we have given the waiting time, a quarter an hour, multiplied by 60. So per trip we charge $15. The new system then have 8 trucks available, that is lambda, and the processing with the 12 trucks per hour, which is automated system process, that is mu here. For WQ, that is 1 over 12 hours. This is the waiting time in the queue. And then to find the new compactor waiting cost, we apply WQ multiplied by 60. That is $5 per trip. So to get a new equipment, we'll subtract the current system by a new system and save about $10 per trip. And for a new cost, charge $3 and saving $7 per trip. The fourth model is finite population model, M bar 1. Here the population of potential customer is limited, and there is a dependent relationship between the length of the queue and the arrival rate. There are some assumptions. Here there is only a single server, the population of the unit asking for this requiring the surface finite, and arrival follows boson distribution, and the surface time are exponential distribution. Customer are always served as first come first served basis. Here lambda is the mean arrival rate, mu is the mean surface rate, n is the size of population because it is finite. We can calculate the probability that the system is empty. We find out average length of a queue, which is LQ, using the formula given here. And also we can find the average number of customers in the system and in the queue, and average time in the system, as well as the probability of a unit in the system. Here is an example of the bottom of Comurance. They have 5 printers and each need to be repaired every 20 hours of work. 5 printers are the population that is given, so capital N is equal to 5, and it follows boson distribution. For a technician can do some surface to a printer, an average of about 2 hours following an exponential distribution. Lambda is arrival rate that will be 1 every 20 hours. So 0.05 printer per hours, as here. And surface rate every 2 hours. They can serve one, so it is 0.5 printers per hours. We use these given values in the equations. Here a capital N is given, which is 5, and there is only one technician on duty. Lambda is 0.05 and mu is 0.5. So we can find P0, LQ, L, WQ, and W. So if the printer downtime cost $120 per hour, multiply by the average number of printers down, which is 0.64, plus the cost of the technician, that is $25 per hour. Total cost will be about $102. There are some general information which have to be given whenever a system starting and enter into what is called a steady state condition. Initially, it will be inside what called as a transient state before things become stabilized. Then when it is stabilized, it's called a steady state. Then the surface and arrival rate will be stable in the steady state approach. There is also a little follow equation, which is LQ to lambda into W, or LQ equal to lambda into WQ. There is a third condition: average time in the system is equal to the average time in the queue plus average time receiving surface. These three formulas can be used to find those variables which are not given to you, unknown variables, by applying to all the equations as before expected the finite population model. There are lots of variation from the basic queuing model, which we stand to be normal probability distribution instead of exponential distribution. We can sort all these things using some simulation to find answers. We can go for simulation if we know they can only be a poor approximation that can be found by normal systems. So computer simulation should be used when standard queuing models provide only a poor approximation of actual surface model. Waiting lines and surface system are important part of the business world. This chapter describes several common queuing situations and present mathematical models for analyzing waiting line following certain assumptions. Those assumptions that our arrivals come from an infinite or very large population. Arrivals are Poisson distribution. Arrivals are treated on first-in, first-served basis and don't bulk or renang. Surface time follow negative exponential distribution or constant, and the average surface rate is faster than the average arrival rate. So the models illustrate in these chapters are for single channel, single phase, multi-channel, single phase problems. Key operating characteristic for a system are shown to be utilization rate, present idle time, average time spent waiting in the system and in the queue, average number of customers in a system and in the queue, and probabilities of a various number of customers in the system. So this chapter emphasizes that a variety of queuing model existing that don't meet all the assumption of traditional model. In this case, we use more complex mathematical model or turning to techniques called computer simulation. At the end, thank you for Dr. Fatima Abu Abdullah for giving me this opportunity, and I am sure this will be helpful in the simulation and modeling subject in the next upcoming semester.